Welcome to the next video of Thermodynamics 2. Today we shall start next chapter, which is chapter number 3, and that is about gas turbine cycles. Alright, so in the previous chapter we discussed the vapor power cycles. Now the next is the gas turbine cycle. It is also a power cycle, but here, as the name indicates, the working fluid is definitely a gas throughout the cycle, unlike in vapor power cycle where you had gas and liquid both phases present at various processes during the cycle. So here one thing is confirmed, that the whole cycle consists of one phase of a substance, and that is actually a gas. So in this case, let me show, for example, now we shall be using the same TS diagram to study these cycles and to perform design calculations of these gas turbine cycles. So on TS diagram, we know for any substance we can show this dome, liquid region, mixed region, and gaseous region, and these are the pressure lines on this TS diagram. Right. So now, as the name indicates, gas, so in this particular case we are definitely in this region, which is totally a gas throughout the cycle. So there is no need to show this dome, right, in these gas turbine cycles, because there is no possibility of this gas to condense during any process, because the temperatures and pressures, they will be well above this phase change region. So we will be far away from this dome in this particular case. So we shall be showing these pressure lines only in the gaseous region, but there is no need to show this dome. So in this whole chapter we will not be showing the dome, only the pressure lines in the gaseous region, like this. For example, this is one pressure line, second pressure line, or third pressure line, depending upon the type of process. Right, so there will be no dome at all because we are in the gaseous region. So that is the major change in this particular chapter. And also, when we are not in the mixture region or near the dome region, we can use ideal gas equations, and there is no need to use steam tables or the vapor phase vapor region tables or mixture region tables. So, and also in these cycles, the working substances, in most of the cases it is air which is burnt in some fuel, and the major portion is of course air. That's why the working substance resembles air throughout the cycle. Right. So this chapter is also mainly covered from this book, chapter 9, 8th edition. We will only study few selected topics of from this chapter, not all the topics in detail, keeping in view the time which is left in this semester, so we cannot cover the whole chapter, so only selected topics will be covered. Okay. So with this introduction, now I shall let's discuss it in more detail. So here it is gas turbine cycle. It is not written here gas power cycle, because gas power cycles does not only mean a gas turbine cycle. There is a difference. Gas power cycle means it could be an Otto cycle, it could be a diesel cycle, or it could be a gas turbine cycle. So we are not discussing diesel or Otto cycle, which that is something which we have already covered. So here we are discussing one particular type of gas power cycle, and that is called gas turbine cycle. So let me explain it here with the help of this figure. Here you see schematics of two different types of commonly used gas power. So this is also a gas power cycle, and that is also a gas power cycle. This first one is used to produce electric power in gas power plant, or the very similar schematic is also used in jet engines. Otto cycle, like this one, Otto cycle and diesel cycle are also gas power cycles, but those consisting of reciprocating movement of piston inside a cylinder, and we have already learned about them in Thermo 1, and also currently you are learning in the Thermo lab also about these reciprocating type of gas power cycles. So in this chapter of Thermo 2 we shall be studying about the gas turbine power cycle, which is not a reciprocating machine, rather it's a rotating machine, or it's a rotodynamic machine. This is not a rotodynamic machine. That is an example of a positive displacement machine, right? Very similar processes in both of these cycles, in both of these gas power cycles. Here first you have the intake, like here intake, then there is compression of this working fluid, which is air. Here also you have a compressor. The difference is here you have a reciprocating compressor, here you have a rotary compressor, right, or axial flow compressor. Next there is combustion, so in here, and also there is a combustion and then expansion of this piston after combustion. So here you have combustion in this case, in this combustion chamber, where fuel is separate, which is actually igniting with the help of this air which was compressed in the compressor. Then air flows through this rotary turbine. Here you have a reciprocating type of turbine, but here it is a rotary turbine. So we use the term turbine only for rotating element. Here we do not use the term turbine. Here it is also producing power, but it is not like this turbine. So here it is the same axial flow turbine which we have discussed in chapter 2. For steam turbines, that is a gas turbine. The only difference is the working fluid. The rest, the working principle of these turbines is very similar to steam turbines. Both are axial flow turbines and rotary turbines. Okay, and then you have this exhaust process, like here in the reciprocating. So both are gas power cycles, but in this chapter we shall be discussing this type of gas power plant, right, which is a rotating machine, not a reciprocating machine. So let's go back. So just like in steam power plant or steam power cycle, the cycle which we studied in steam power plant, that was Rankine cycle. Similarly, in gas power cycle, the name of that cycle which describes the working principle of a gas power cycle is called as, or is known as, Brayton cycle. So just like we discussed about ideal Rankine cycle, so here, which is an ideal cycle for vapor power cycle, similarly here the ideal cycle for gas turbine engines is actually known as Brayton. Brayton cycle was actually first proposed by this person. The name of that person, it is known as Brayton cycle. So initially Brayton used this cycle in reciprocating oil burning engines around 1870. So initially it was a reciprocating type of engine, but today the same process or the same cycle is used for gas turbines, which is not a rotating element. It is a which is a rotating element, not a reciprocating type of machine. So here both compression and expansion process takes place in a rotating machine, but in case of reciprocating type of gas turbines or gas power cycles, both compression and expansion processes, they take place in reciprocating type of cylinder piston mechanism. Okay, so how the cycle look like? Here you see the processes of this Brayton cycle. So here what is happening, fresh air or ambient air at ambient condition is actually drawn into this compressor. So here what happens, the temperature and pressure of this air increases from some initial temperature and pressure to the final temperature and pressure. So here the working substance is throughout gas. In case of Rankine cycle, this task was performed by a pump and it was throughout liquid, but here it is throughout a gas, right? So that is explained here. Next is now the pressure, high pressure, high temperature air is now entering into a combustion chamber. So this high pressure, high temperature air enters into this chamber where fuel is separate over this compressed air whose temperature and pressure is already higher. Now this fuel will burn due to the presence of this air, right? And now because of this burning of this fluid, after reacting with this air, and actually it is mainly the oxygen present in the air which reacts with this fuel. Nitrogen does not react, and the major portion is actually nitrogen which remains as it is, and it does not take place in the does not take any share in the reaction of this fuel, right? So this high pressure, so it's the major portion in this combustion chamber is still air. For example, if there is 1 kilogram of fuel which is separated here, so there would be about 15 or 20 kilograms of air, depending upon the type of the fuel. This air fuel mixture could have different value, but in any case the amount of air to burn 1 kilogram of fuel would be much larger than the fuel. So the working substance still resembles air. So after this chemical reaction, the temperature of these gases further increases, but during this heat transfer process or the combustion process, only temperature rises, pressure remains constant. Ideally we assume that the pressure does not change. Here mainly the temperature rises to a very high value, right? So here it is written, the high pressure air proceeds into the combustion chamber where the fuel is burnt at constant pressure. Right. So the next is the turbine portion. So now this resulting very high temperature gases enters into a turbine. So we know how the turbine works already. We have studied about it in steam power plant. So it is a very similar type of turbine. So here you see from inlet till exit, the height of the blades are increasing. That's why it is shown like a conical shape from inlet till exit. Why height increases we already discussed in chapter 2. So this resulting high temperature gases enters into this turbine where they expand because they are doing work on to these blades, and blades are attached to the shaft is attached to a generator, and this network output of this shaft is actually converted into electricity, right? And this here you can also see this turbine is also connected to a compressor. So a small portion of this work output of this turbine is actually fed to the compressor also because we need power to run this compressor. So the total power which is produced in the turbine, a part of it is reused here in the compressor to compress the air, right? That is explained here. Now after performing work, those gases leave the turbine and those are actually thrown out, and it is not recirculated because these are exhaust gases, and these gases are different from this air, fresh air, and it cannot be reused. And so this is not actually a closed cycle, it is an open cycle because we are not using this working fluid again to complete a cycle, that as it was in the steam power cycle. In case of steam power cycle, the same steam was reused, right, in the whole cycle. So that was definitely a closed cycle, but actually this gas power cycle is not a closed cycle, it is an open cycle. Mass is entering and then mass is leaving, right? So that is written here. The exhaust gases leave the turbine, are thrown out, not circulated. That's why it is an open cycle. Yeah. So these open gas turbine cycles can be modeled as closed cycle by using the air standard assumptions. So if you remember, we used those air standard assumptions. We learned about these assumptions in Thermo 1 in the last chapter. So if you remember what we did there, that we replaced this combustion process with simple heat addition process, and this exhaust process as heat rejection process. So these are the air standard assumptions which we discussed and studied in the last chapter of Thermo 1. So if you do not remember, just go through those air standard assumptions. So if we apply those air standard assumptions on this ideal gas cycle, so now our cycle would look like this one, right? So after applying those air standard assumptions, so now it is a closed cycle. So here we are assuming it is throughout gas, throughout air. So there is no combustion phenomena. We have replaced this combustion phenomena with heat transfer process, just like heat exchanger. So heat is transferred to this working fluid, which is pure air, and similarly here the exhaust process is replaced with heat rejection process, that this fluid is actually rejecting heat to the ambient and then it is reused. So the actual process is assumed like a closed process, a closed cycle, thermodynamic cycle. So this will ease our mathematical calculations. So I'm telling you again, if you do not remember why we are doing it, so just go to chapter 8 of thermodynamics 1, where we have studied about these air standard assumptions. Based on those air standard assumptions, this is the resulting cycle. So now let's see again those processes. So here in these air standard assumptions, compression and expansion process remain the same as it was here. There is no change in the compression and expansion process in the compressor and in the turbine, right? The difference is here, the combustion process is actually replaced by a constant pressure heat addition process from an external source. Similarly, the exhaust process is replaced by a constant pressure heat rejection process to the ambient air. So these are the two major changes in this cycle. So ideal cycle that the working fluid undergoes in this closed loop, this ideal cycle which we have assumed, is known as the Brayton cycle, right? So in case of steam turbines, if you remember, those turbine rotates in the currents which are caused by the hot water vapor here in this case. So it was actually a hot water vapors which were doing work in this turbine, and they form a part of a closed water cycle in which water condenses here and is then heated until it evaporates here. So steam turbines therefore do not come into contact with the fuel, right, which is burnt outside this heat exchanger. And the maximum temperatures in case of steam turbines is around 500 to 600 degrees Celsius. So several steam turbines are often arranged in a row, so that we have seen that there, in case of steam turbines, this turbine can be converted into actually consist of 3 stages: low pressure stage, intermediate stage, and high pressure stages, so that we can extract the power of this steam in a more efficient way. So but in case of gas turbines, on the other hand, they rotate directly in the hot combustion gases. So in case of steam turbine, it was steam, the combustion gases was outside, but here in case of gas turbines, these turbine blades actually are rotating in those hot combustion gases which are burnt here. And here in case of gas turbines, the temperature at point 3 could be well above 1000 degrees Celsius, 1000 or 1500 degrees Celsius, right? So these gases are much hotter than those are in the steam turbine. In the case of steam turbine, the maximum temperature is about 500 to 600 degrees Celsius. So that's why, for this reason, the blades which are used in case of gas turbines, they need to be cooled with air that flows out of some openings, small openings, and creates a protective film between the exhaust gases and the blades. So without cooling the blade material, this will quickly wear out, right? So in the case of gas turbines, we need the cooling of the blades because the temperatures attained here are very high, right? So the maximum pressure in case of gas turbines, the maximum pressure means this pressure 1 to 2, and then 2 to 3 pressure remains constant. So here is the maximum pressure in case of gas turbines. This maximum pressure in case of gas turbines are quite low compared to steam turbine, because in case of steam turbine we have seen this pressures could be more than 22 megapascal, but in case of gas turbines these pressure rise is not so huge. But in case of gas turbines this temperature is very high. In case of steam turbines, this temperature, maximum temperature was low, but pressure was very high during this process. But here in case of gas turbines, the pressure is not that high compared to steam power plants, but temperature at this point at the entrance of turbine is very high. Right, so maximum pressure in gas turbines are very low compared to steam turbine inlet pressures, but maximum temperatures in gas turbines are very high compared to steam turbines. So that's why the steam turbines in case of steam has to face very high pressures, while in case of gas turbines they have to face very high temperature, not pressure. So, and that's why the metallurgical designs of both turbines are quite different, because in case of steam turbine blades they are designed to sustain very high pressures, not very high temperatures, but in case of gas turbines they are actually designed to sustain very high temperatures and not pressures. Okay, these are very the details which are not required at this point. So in some advanced course we can further discuss about the designing or metallurgical designing of these turbine blades. Okay, so now we can represent this cycle on TS diagram. So let's start from point 1 to point 2. So for an ideal cycle, 1 to 2 process is compression, and ideal compression process would be isentropic. So that is clear from, and these are the pressure lines. Here we are not showing any terms. So 1 to 2 represents the isentropic compression process, then 2 to 3 represents the heat addition process, but during this process temperature increases but pressure remains constant and heat is added, right? 2 to 3. So actual combustion process is replaced with simple heat addition process. Then 3 to 4 inside a turbine, and again inside a turbine there is expansion of gas, and expansion process can be shown by a vertical line, again isentropic expansion. Then 4 to 1 there is heat rejection. So during heat rejection means heat is transferred, so entropy cannot remain constant, entropy actually drops but at constant pressure. So these are the pressure lines in gaseous region, right? So hopefully if you have a very clear idea how the pressure lines look like in the gaseous region, then you can easily draw this TS diagram for gas power cycle, and how the pressure lines change their directions for inside a dome. So that's why the pressure lines variations were quite different in case of steam turbines. Okay, so the same process can be shown on PV diagram, right? Pressure versus volume diagram. Here 1 to 2 process was isentropic, but during 1 to 2 process is actually compression process. So during this compression process pressure and volume both changes. So that's why 1 to 2 process is a curved line, unlike here it is a vertical line, because during this process entropy remains constant but pressure rises and volume drops. So that's why on PV diagram 1 to 2 line is shown as a curved line. Then 2 to 3 process is a constant pressure process. That's why here you see 2 to 3 constant pressure line on PV diagram, unlike here 2 to 3 process was constant pressure but pressure lines were curved lines. So that's why 2 to 3 is exactly a straight horizontal line, unlike here on TS diagram 2 to 3 is a curved line. Then 3 to 4 process is occurring inside turbine, again isentropic, but inside a turbine what is happening to pressure and volume? Pressure is dropping 3 to 4 on y-axis. We can see there is a drop in pressure, but at the same time when pressure is dropping, volume is increasing. So that's why from 3 to 4 volume is increased. And then 4 to 1 is again a heat rejection process at constant pressure. When heat is rejected, volume again drops, or the gas compresses or contracts while it is losing heat or it is getting cooled down. Right. So I think the TS and PV diagrams are clear. We have discussed these diagrams for Otto and diesel cycle in Thermo 1 also. So okay. So now this is the Britten cycle, which is made up of 4 processes which are internally reversible. That's why those are shown with solid lines. So for an ideal cycle, we have to assume those are internally reversible at least. So 1 to 2, in a pure thermodynamic way, we will call it isentropic compression in a compressor. Then 2 to 3 is isobaric heating or constant pressure heat addition. Right. Then similarly 3 to 4 is isentropic expansion in a turbine. Right. 4 to 1 constant pressure or isobaric heat rejection. 4 to 1. Okay. Now let's do thermodynamic analysis. So thermodynamic analysis means we want to derive the thermal efficiency equation similarly to steam power cycle, where we have derived the efficiency equation. So the general definition of efficiency is the same, that it is equal to 1 minus Q out over Q in, or network output divided by heat input. So heat transfer to and from the working fluid R, where is the Q in? This is the process 2 to 3, Q in. And we can find out this Q in from enthalpy change, H3 minus H2, right? And in this case, it is throughout a gas. There is no phase change process. So throughout a gas, and if we assume specific heat remains constant, so this delta H, H3 minus H2 can be calculated directly from Cp delta T. We don't need any tables or charts to find out these values of enthalpy from at point 2 and 3. We can simply use Cp delta T because it is throughout a gas. Right. So Qn is simply H3 minus H2 is equal to Cp into T3 minus T2. Every term is written for 1 kilogram of mass. So capital Q will be equal to m dot into delta H, H3 minus H2. Similarly, what is Q out? Q out is the enthalpy change, H4 minus H1, or Cp into T4 minus T1. Right. So now we can write the equation of thermal efficiency, which is for this ideal Britten cycle, right? And that is given by W net over Q in, or 1 minus Q out over Q in, thermal efficiency of Britten cycle. Now let's put values of Q out or Q out and Q in this equation. So here is the now Cp, assuming Cp remains constant throughout the cycle, so Cp will cancel with Cp. So now we have the thermal efficiency of Britten cycle only in terms of temperatures. Now we'll do certain mathematical manipulations to write this equation in a more simplified form. So what is done here, T1 is taken common here, T2 is taken common from the denominator, so that mathematical step is clear. Now we shall further simplify. Now you see this process, 1 to 2 is isentropic and 3 to 4 is also isentropic, and P2 pressure is equal to P3 and also P4 pressure is equal to P1, right? So that is written here. Now for isentropic process, we also know some more equations for an ideal gas and for an isentropic compression or expansion process. We derived these equations, right, for constant specific heat, for ideal gas, and for isentropic process. We can write this compression equation as this one, right? So this is something which we have derived in Thermo 1 chapter 7. So that is clear. Now P2 is equal to P3 and P1 is equal to P4. So we can write the same term as in terms of P3 P4, because P2 is equal to P3 and P1 is equal to P4. Now what is 3-4 process? 3-4 process is also isentropic, so it means this pressure ratio to the power k minus 1 over k is also equal to T3 over T4. So overall, this equation is telling us that T2 by T1 is equal to T3 by T4. So if we cross multiply this term, so then we can write it as T4 over T1 is equal to T3 over T2. Means T4 over T1 is equal to T3 over T2. Right? This implies that. So now it means this term will cancel with this term. So efficiency of this ideal Brayton cycle will be equal to 1 minus T1 over T2. And what is T1 over T2? T1 over T2 can be written as P1 over P2 to the power k minus 1 over k. Right? So T1 over T2, 1 minus, now efficiency is equal to 1 minus T1 over T2, and we can write this term, because this cancels with this one. This can be written as 1 minus 1 over T1 over T2. So this term can be written like this mathematically, and this T1 by T2 can be replaced with this term. Right. So this will be equal to P2 by P1. And that is this P2 by P1 is the pressure ratio, and that is represented by RP. Right. I think there is one mistake. Yes, it will be T2 by T1. Yes, when you write this term like this, 1 over, so it will be T2 by T1. When we will take this term in the denominator, its power will be minus 1. So which means that will be T2 over T1, not T1 over T2. And T2 over T1 is equal to P2 over P1 to the power k minus 1 over k. And this P2 over P1, which is a pressure ratio, the rise in pressure in the compressor, this pressure ratio is represented by, RP. So that's why this equation changes to this equation. Right. So now we have efficiency of Brayton cycle only in terms of pressure ratio and K. What is K? K is specific heat ratio, Cp over Cv. Because in case of gases, Cp and Cv are not equal, and their ratio is known as specific heat ratio. Right. So now we have efficiency of so where Rp is equal to P2 by P1 and K is the specific heat ratio. So now we have thermal efficiency of Brayton cycle simply as a function of pressure ratio and specific heat ratio. So under these cold air standard assumptions, the thermal efficiency of Brayton cycle depends upon the pressure ratio of the gas turbine. Pressure ratio means this pressure rise from 1 to 2, and that is equal to 3 to 4. Right. These pressure ratios, and the specific heat ratio of the working fluid. Working fluid, if it is more, in most cases it is air, right, or a fluid which is resembling air, right. And also remember, in case of gas turbine cycles, the fuel which is burnt, it could be a liquid fuel or it could be a gaseous fuel. In case of gaseous fuel, it is more, in most of the cases it is natural gas, right. So whether it's a liquid fuel or a gaseous fuel, after burning it becomes a gas throughout, and major portion is because it's air, so that's why we can assume throughout air in this cycle. So the thermal efficiency, we can see from this equation, thermal efficiency increases with both by increasing this Rp because in the denominator 1 minus 1 over this term. So by increasing this Rp or K, this efficiency will increase, right? And that is the case in, because this is the efficiency equation for an ideal Brayton cycle. So ideal Brayton cycle is telling us that the efficiency of this cycle is mainly dependent upon these two terms. So in actual cycles also, these two parameters will have a huge effect on the thermal efficiency. So the thermal efficiency increases with both pressure ratio and K, which is also a case in actual gas turbines also. So now if we draw a curve between these two terms, for example, by keeping the K constant, for example, for air K is 1.4, and then changing this Rp, the pressure ratio, by increasing pressure ratio from 0 onwards, we can draw a curve. So by assuming different values of Rp, 1, 2, 3, 4, 5, and by taking K constant, we can find out efficiency, and if you draw this efficiency, we'll get such a curve, right? So here you can see as the pressure ratio is increasing, the efficiency is also increasing, reaches a here maximum value, and then it will not increase anymore. So that's why the pressure ratio is normally chosen in this region. What is this region? Between 5 and 20. So depending upon a particular design or the overall capacity of a thermal power plant, it is normally chosen between 5 and 20. So highest temperature in the cycle occurs here at this point at the end of combustion process, means at point state 3, and this point is again maximum temperature is again limited by the temperature, the type of or the material of the turbine blades which can withstand such high temperatures. Okay, so now let's further analyze. Now for a fixed turbine inlet temperature, now what this means? For example, I draw a curve on TS diagram. Now we know this is the Brayton cycle, right? And this is the maximum temperature. Compression, isentropic compression, then heating, constant pressure heating, then 3 to 4 represents isentropic expansion, and this is the maximum temperature. For example, this maximum temperature is limited, that should be 1000 Kelvin, right? So you have designed your blades which can withstand this temperature. So now here we can analyze the effect of pressure ratio. What is this pressure ratio? This P2 over P1. So now maximum temperature is fixed, that is 1000 Kelvin. Now we can see what could be the effect of increase in pressure ratio. So here it is written, for a fixed turbine inlet temperature, that is the turbine inlet temperature, the net work output is this area, right? Because area under 2 to 3 represents heat transfer to the system, area under 4 to 1 represents heat transfer out of the system, and Q out minus Q in represents this area, and that is the network output of this cycle. Okay, so now what is written here, that the for a fixed inlet temperature to the turbine, this net work output per cycle of this cycle increases with increase in pressure ratio. So for example, if you increase this pressure ratio till this point, and then there is heating process, but you cannot go beyond this value, and then there will be expansion and then heat rejection. So we would see, it is not drawn on scale, that this area will increase, right, compared to this area. If you further increase this pressure ratio, for example, till this point, and then heating is only till this point, and then this is expansion in the turbine. So now this area becomes smaller. So with the increase in pressure ratio, we shall see, if we draw it on scale, that with the increase in pressure ratio, this network area increases, reaches a maximum value. For example, this is the maximum value. Then it starts to drop if you further increase the pressure ratio by keeping this maximum temperature same. Right? That is limited by the metallurgical requirements of the blades. So that is what is I'm trying to explain the meaning of this sentence, right? So this diagram is also shown separately. So here you see the same diagram which I draw roughly. So here you can see the effect of pressure ratio. This was the lowest pressure ratio, then this was heating to reach the same maximum temperature, then isentropic expansion, then heat rejection, right? Now if you increase the pressure ratio to this point, now the heating in the combustion chamber, then expansion in the turbine, and then it completes the process. So from this to this, as the pressure ratio is increased from 2 to 8.2, for example, your this network output increases. If you further increase this pressure ratio, for example, this 0.2 ends up here, then this will be the heating process to reach the same maximum temperature of 1000 Kelvin, and then this will be the expansion process, and that is the heat rejection process. So we shall see that this area, network area, is continuously increasing as the pressure ratio is increasing, reaches a maximum, and then it starts to drop, right? And where will be this maximum? This maximum will occur at this point when the pressure ratio is equal to, for a fixed T minimum and T maximum temperature. For example, this T minimum is fixed and this T maximum is fixed, right? So this maximum will occur at this point, at this pressure ratio. Rp is equal to T maximum over T minimum to the power K over 2 into K minus 1, right? So this will be that maximum pressure ratio at which this maximum will occur. Maximum efficiency or maximum network output will be obtained. So below this value or higher than this value given by this equation, the efficiency will be dropped or network output will be less. So that is that maximum point which was also shown here, that is that maximum, right? But by increase in pressure ratio, of course you have to build a huge compressor, so also the cost matters, the metallurgical requirements also matters. So normally it is not operated at this maximum pressure, because then RP pressure ratio would be very high, so a little lower than this value or in this region which is economically feasible, right? So that is clear. So there should be a compromise between the pressure ratio, because by increasing pressure ratio, efficiency increasing, but it reaches a maximum and then it starts to drop because the network output starts to drop. So we have to compromise between these two values. Pressure, with the increase in pressure ratio, efficiency is increasing, but reach at a certain pressure ratio it becomes maximum and then it starts to drop. So with less work output per cycle, so for example you get a very less work output from this cycle, and we also know that when we represent a cycle on TS diagram or on any diagram, we are representing actually 1 kilogram of mass. So if the work output from this cycle is very low, it means you have to increase the mass flow rate, because the network output is given by the enthalpy changes, and enthalpies are for 1 kilogram of mass. So work output or heat input or heat rejected is actually m dot into delta H. Actually heat input is m dot delta H, right? Work output during this process is also given by m dot into delta H, right? So from this diagram we can also only find out what is delta H. If this delta H very small, then you have to increase m dot to get your required overall power. that is with less work output per cycle for 1 kilogram of mass, a larger mass flow rate, thus a larger system is needed to maintain the same power output, which may not be economical, because when you increase the mass flow rate to get the higher power, then the work output increases, but then also work input increases, because the same mass is also flowing here in the compressor. So you have to give more work to the compressor also, and more heat in the combustion chamber, because M is very high. So depending upon the overall output and the cost requirement, it has to be optimized. So in most cases, this pressure ratio of gas turbines is normally taken in this range, 11 to 16. Now air in this gas turbines performs two important functions. One, it supplies of course the necessary oxygen or oxidant for the combustion of the fuel during this process, 2 to 3. And also there is a second purpose, because we have seen here this temperature is very high compared to steam power cycle. This temperature is quite high, about 1000 or above 1000 degrees Celsius, right? So this air also serves as a coolant to keep the temperature of various components in like combustion chamber and the gas turbine components to a safe limit. So this air is in the gas turbine is not only providing oxygen for the combustion, but this air, extra air, is also acting as a coolant. Right. So for example, to burn 1 kilogram of mass we need 20 kilograms of air, but here in gas turbines power plants or in a gas turbine cycle we supply 50 kilogram of cycle. So only 20 kilogram is used to burn the fuel. The rest 30 kilogram will be used to cool these components, because this air will not burn, so its temperature will remain low. So it will not make the temperature of the burnt gases to a very high value, right? So that's why in those cases in gas turbines an air fuel mass ratio or air fuel mixture, their ratio could be around 50 or even above 50, right? Air to fuel mass flow, air to fuel ratio could be in this range, 50 or above. Out of those 50, maybe only 20 is needed to burn this fuel. The remaining 30 is only used to maintain, to keep this maximum temperature in a safer limit, right? Because this temperature could go very high and that will damage the turbine blades. That's why the amount of air which is circulating in these turbines is quite high. The amount of air is very high compared to the amount of fuel which is injected. That's why it is a good assumption to assume air throughout, right? So in a cycle analysis, in the analysis of these gas turbine cycles, if we assume these combustion gases as air, does not cause any error, because actually it's not air, it is a combination of gases. So we have discussed this thing in a number of places, in a number of times in Thermo 1 also. So let's go forward, sorry. Okay, now we have also learned about this back work ratio in case of steam power plant. The two major applications of gas turbine engines, such engines, are of course for aircraft propulsion. Second is to produce electric power generation. So here so far we are discussing the gas turbine cycle which are used for electric power generation, right? So back work ratio, the ratio of this compressor work to the turbine work, because a major portion of this turbine work is reused here in case of compressor. It was liquid in case of turbines, that's why there was a pump. So since it was a liquid which is compressed in case of steam power plant here instead of a gas, and therefore steady flow work is proportional to the specific volume of this working fluid, V into P2 minus P1. We used to calculate the pump power because specific volume was not changing. But in case of this gas compressor, this V does not remain constant, so there will be a change in specific volume with pressure also, That's why the work output will be, the work input to the compressor will be very high compared to the equivalent work input in case of liquid pump. So in gas turbines power plants, this back work ratio is very high because a significant portion of this turbine is reused here in case of to run this compressor, right? So more than half, it could be more than half of this turbine work output is used to derive the compressor. But in case of steam turbines, this was very small value. That's why steam turbines are have this huge advantage over gas power cycle, because the back work ratio in case of steam power plant was a very small value. So here you see almost half of the turbine work is reused to derive this compressor. So this is a very high value in comparison to steam power plants, where this back work ratio is only a few percent. So right, so this back work ratio can be defined as ratio of net work output of the turbine. Net work output means the work output of turbine minus work input to the compressor is the net work out of the turbine to the gross work output of the turbine. Gross work output means the total output of the turbine. Right, so the back work ratio can be defined like this one or like this one. So a power plant with a very high back work ratio, like these gas power plants, right, requires a larger turbine to provide the additional power requirements of the compressor, because here a significant portion of this turbine work is reused, and so that's why these turbines are made very large or very bigger, because we want to extract a huge amount of W, so that if more than 50% is reused here, so your required power is still obtained. So to obtain the required network output after delivering this energy, a significant energy to the compressor, these turbines, gas turbines, are much larger in size, right, to get the same power output as from an equivalent steam power plant. So that's why turbines used in gas turbine power plants are much larger than those used in steam power plants of the same net power output. Right. Next, we shall now see the actual gas turbine cycle. So far we have seen the ideal gas turbine cycle. So just like in steam power cycle, the actual cycle will differ from the ideal cycle due to irreversibilities in various processes. So that is shown here. So the irreversibilities in the compression and expansion processes are clear. The actual process will be non-isentropic, right? 1 to 2A represents non-isentropic compression in the compressor, and 1 to 2S represents ideal or isentropic compression. Similarly, in the turbine process, which is the expansion process, ideal process is 3 to 4S, isentropic expansion, and 3 to 4A is the non-ideal or non-isentropic compression. So these are the irreversibilities in the compression and expansion processes, which are shown here in the form of non-isentropic processes. Now the major irreversibility in case of combustion chamber or heating process and cooling process is the pressure drop, right? So pressure does not remain constant at this point 2A. It drops to lower pressure 3 due to the fluid friction while it is flowing through the heating system, which is a combustion chamber. Similarly, there is pressure drop in the heat rejection process. So these are the major irreversibilities found in the actual cycle, due to which the ideal system differs from the actual cycle. So it is actually the pressure drops in the heat addition process and pressure drops in the heat rejection process, and a non-isentropic and non-isentropic compression and non-isentropic expansion in the compressor and turbine process respectively. Normally in the design calculations, we neglect the effect of these pressure drops in the heater and cooler, and these Non-isentropic effects are accounted for compressor and turbine by defining the isentropic efficiencies. Right. So why the actual cycle differs from the ideal cycle due to irreversibilities in turbine and compressors and pressure drops and heat losses. Right. Heat losses means the heat losses in the combustion chamber to the ambient, or heat losses in the heat rejection process, and also heat losses in the pipes or passages connecting these four main components with each other. So isentropic efficiencies of the compressor and turbine, we have already learned how to define the isentropic efficiency of turbine and compressor. In the case of compressor, the isentropic efficiency will be equal to the isentropic work, which is less, divided by actual work, which is more work input to the compressor. Similarly, for turbine, it is actual divided by isentropic. So that is something which we have already discussed in the chapter of steam turbines. Right. So these are the isentropic efficiencies for compressor and turbine to account for the frictional losses. Okay. So now we shall solve a numerical problem. Gas turbine unit has a pressure ratio of 10 to 1. So pressure ratio 10 to 1 means the pressure which is raised in the compressor P2 by P1, and the maximum cycle temperature is 700 degrees Celsius. This temperature, maximum cycle temperature, which occurs at the inlet of turbine or at the exit of combustion chamber. Right. So this will be T3 at the inlet of turbine. The isentropic efficiencies of the compressor and turbines are given. Here are the isentropic efficiencies of compressor. This is isentropic efficiency of compressor 0.82 and isentropic efficiency of turbine eta T. And we have just defined their equations. Next is to calculate the power output of an electric generator geared to the turbine when the air enters the compressor at 15 degrees Celsius. So at the inlet of compressor, the very starting point, that is T1, at a rate of 15 kilograms per second. So fluid is flowing through this turbine at a rate of 15 kilograms per second. Take Cp of air as 1.005 kilojoules per kilogram per Kelvin, and gamma, or specific heat ratio, for air is 1.4 for the compression process. And so here Cp of air for the compression process is 1.005, and take Cp is equal to 1.11 and gamma is equal to 1.33 for expansion process, because during expansion at the inlet of the turbine the temperature will be very high and Cp value will change because Cp changes. Cp is a function, Cp and gamma both are functions of temperature, and at the inlet of compressor or during the compression process the temperatures are quite low compared to the temperature which is at the inlet of a turbine. So now we need to calculate the cycle efficiency and the back work ratio of this plant, assuming Cp for combustion process. During combustion process where temperature is increasing, right, the Cp value is 1.11. We can take the process during heating. The Cp value during heating process can be taken as 1.11 kilojoules per kilogram per Kelvin. So in this problem, the value of Cp is not a constant for the whole cycle. For various processes, we have to choose different values of Cp, right? During compression process, then during expansion process in the turbine, and during heating process in the combustion chamber. So these are the three different values of CPs. So first of all, in thermodynamics, we will draw the schematic diagram. So here is the schematic. It's a simple Britten cycle. Simple ideal Britten cycle is drawn here. The schematic. So here is the T1. So temperatures should be in kelvins because we would be using ideal gas equations. So in ideal gas equations, the temperature should be in kelvins. So T1, T2 is not known, T3 is given maximum possible temperature, which is 700 degrees Celsius, right? In Kelvin it is 973. So 0.1, 0.2, 2 to 3, 3 to 4, it's all clear. Turbine is connected to a generator. Turbine is also connected to the compressor also. So now we can show the same process of schematic on TS diagram also. So 1 to 2S is the isentropic compression, 1 to 2 is actual compression, 2 to 3 is isobaric or constant pressure heating in the combustion chamber, then 3 to 4 is isentropic expansion in the turbine, and 3 to 4 represents the actual expansion in the turbine. So just like in case of steam power plants, we need to calculate enthalpies at all of these points. So the same procedure will be adopted here, but here we can calculate enthalpy by Cp delta T. So it means we need to calculate temperatures at each of these points because CPs are given, right? So we need to calculate all the temperatures at point 1, 2, 3 and 4. And the actual points we have, because here isentropic efficiencies of compressor and turbine are given, so that's why we have to calculate actual T2 and actual T3, T4 and so on. So T1 and T3 are given, so we need to calculate T2 and T4, and then we can calculate the efficiency of this power plant or the back work ratio. So the process and this compression process is isentropic, 1 to 2s. For isentropic process, we know this equation, T2s over T1 is equal to P2 over P1 to the power gamma minus 1 over gamma. So by putting the values, P2 over P1 is given 10 by 1. So from here we can calculate T2. That comes out to be 556 Kelvin. Now we can find out, so this is T2s. So with the help of this T2s, we can find out actual T2 by utilizing the compressor isentropic efficiency formula, and that is given by this formula. Efficiency of compressor is H2s minus H1, which can be written as Cp into T2s minus T1. Cp will cancel in the denominator and the numerator because during the whole compression process Cp is constant as 1.005. So isentropic enthalpy change divided by actual enthalpy change. So it is actually enthalpy changes where Cp has cancelled. That's why we have efficiency only in terms of temperatures. Now this is given 0.82. T2s is already calculated. T1 is also known. So now from here we can find out T2. Right. So by putting values, T2 is calculated to be 614.8 Kelvin. Next, similarly, now we have calculated T2. Now we need to calculate T4. So the same procedure will be adopted in this case for expansion process in the turbine. It is again isentropic process from 0.3 to 0.4s, which is equal to P2 by P1 because the pressure is same. P2 is equal to P3, P1 is equal to P4 or P4s. So the same pressure ratio will be utilized here, right, to the power gamma minus 1 over gamma. Right. So here by putting values, so the difference is here. For this case, gamma was 1.4. But for this expansion process at a higher temperature, gamma is taken as 1.33, which is given here, 1.33 for expansion process. So by putting values, so now we can calculate T2s, T4s, then with the help of this T4s, we can find out T4 from this isentropic efficiency of turbine. So just simply by putting values we can find out T4, which comes out to be 611.2 Kelvin. Okay. So now T4 is calculated. Now we can find out the work of a turbine. Work of turbine will be H3 minus H4 or Cp into T3 minus T4. So we can calculate work of turbine from this equation, Cp into T3 minus T4. So by putting values, all the temperatures are known. So here is the work of turbine. M dot is not multiplied, so that's why the final answer is in kilojoules. That is joules, kilojoules per kilogram, 401.6. Similarly, we can find out work of compressor. The same formula. Now H2 minus H1, work of compressor is equal to Cp into T2 minus T1. Right? By putting values, so here is the work of compressor in kilojoules per kilogram. Now the work of turbine minus this work of compressor will be the net work output, because turbine of a major portion of this turbine work out of this 401.6, 328.4 will be reused to derive this compressor. So net work output will be subtraction of these two values. So the net work output is only 73.2 kilojoules per kilogram. Alright, so now we can find out the net work output in kilowatts, because that is the net work output for 1 kilogram of mass. So the net work output for the whole mass, which is 15 kilograms per second, m dot, which is flowing in this cycle, is not 1, it is 15 kilograms per second multiplied by 73.2 kilojoules per kilogram. So that is the work output or power output of the turbine, which is fed to this generator, and that is 1098 or 1100, about 1100 kilowatts. Okay, so next we calculate the heat which is transferred during this boiling process, means, sorry, not boiling, it is a heating process, or inside the combustion chamber, that is Cp into T3 minus T2. So by putting values, we can find out this heat transfer per unit mass, that is 397.6 kilojoules per kilogram. We needed this Q to find out the efficiency, because the next part, the next question was to find out the efficiency of this, thermal efficiency of this power plant. So now efficiency is given by net work output per kilogram divided by this Q. So next efficiency comes out to be 18.4%. Right, now the back work ratio is work of compressor divided by work of turbine, which we have already calculated for 1 kilogram of mass here and this term. So the back work ratio comes out to be a very high value, 0.82. So that is the issue with these power cycles, that the back work ratio is very high. So that's why to get the same amount of power, we have to increase the mass flow rate significantly, because we can get only 73.2 kilojoules from 1 kilogram of mass, and to get the required power of for example, here in this case it is 1100 kilojoules in 1 second, we have to multiply with a huge amount of m dot, which is 15 kilograms per second. So 15 kilograms of fluid or air has to flow through this turbine in every 1 second to get 1100 kilowatts, because from 1 kilogram we can get maximum of 73.2 kilojoules, but we want to have 1100 kilojoules in 1 second. So that's why the mass flow rate has to be 15 kilograms per second. So we can calculate the same back work ratio from this formula also. The net work output, which is this one, 73.2 divided by work of turbine. So the total work output of the turbine is this one, and this is the net work which is supplied to the generator. So the same work ratio, back work ratio, can be calculated from this formula. sorry, the back work ratio is the amount of energy which is supplied to the compressor, and simple work ratio is another term, right, which shows us that how much is actually supplied to the generator, right? So W net work output divided by total work of the, or gross work output, network output divided by gross work output, and gives you a simple work ratio, and that is back work ratio. These are two terms which are used in the gas power cycles: work ratio, back work ratio, thermal efficiency, right, and of course network output. Now let's quickly go through the aircraft engines. The aircraft engines, or the jet engines, in which we actually use a nozzle also. So it is it is also operating on the same Brayton cycle, but with the difference that at the end of the turbine there is a nozzle also. The rest of the cycle is very much same as the power cycle to produce electric power. So here is the Sachimetric, the same air entering, ambient air entering into the compressor, then it, after it gets compressed, temperature and pressure rises. Now it enters into combustion chamber. In the combustion chamber, temperature rises, pressure stays same. Then it enters into a turbine where a part of this turbine work is used to derive this compressor. But at the end of the turbine, now fluid enters into a nozzle, and this is the major function in the case of a jet engine, the rise in kinetic energy of the fluid in the nozzle. So the turbine output is only used to derive the compressor, right? And the major enthalpy change should be here, because that is the enthalpy change or kinetic energy rise which will give the desired thrust in this direction, right? The aircraft motion is in this direction. So jet engines operates on the same Brayton cycle, with one change, that at the end of the turbine there is a nozzle. Right. So this is the simplest form of jet engine, which is called turbojet. Right. There are also turboprop and turbofan engines. So this one is a turbojet engine. So turboprop engine will have, here in the next slide we shall see, there is also a propeller. So that propeller will give extra thrust, right? So to take the larger weight, to carry a larger weight like C-130, such airplanes where we need to have a more thrust to take a huge amount of weight, then we also use a propeller. So we'll see in the next slide. But without propeller, then it is a simple turbojet engine, right? Okay. So now we shall see the TS diagram, right? So here is the TS diagram of this cycle. So 1 to 2, again isentropic compression, actual compression. 2 to 3, constant pressure heating in the combustion chamber. 3 to 4, again isentropic expansion. 3 to 4 is actual compression, expansion. 3 to 4, and now at point 4 it enters into the nozzle. So here is the remaining enthalpy drop, 4 to 5s and 4 to 5. So this enthalpy drop is actually converted into kinetic energy rise, so which you already know how the nozzles operate, right? So the aircraft is powered by the reactive thrust here of the jet of gases which are leaving the nozzle, and this high velocity jet is obtained at the expense of this enthalpy drop from 4 to 5. So this enthalpy drop is the actual useful process for this turbojet engine, right? So the turbine develops just enough work to derive this compressor and to overcome mechanical losses, right? So the purpose of turbine is not to produce electricity in this case. Here you see another type of turbojet engine which is called turboprop engine. So turbine here derives not only the compressor but also this air screw or propeller. Right. So engine uses the propellers here instead of nozzle. We may use this propeller to produce more thrust. So usually used on large cargo planes. Propellers cannot go supersonic. Like in case of nozzles. In case of nozzles, we can attain supersonic velocities. Why we can obtain supersonic velocities? This is very much clear in chapter 1. We can design nozzle as convergent divergent nozzle to attain supersonic velocities. But here, there is no nozzle after the turbine. Here the turbine work is actually used to derive this propeller, and this propeller is actually making this air to flow in this particular direction or to change the velocity of air in this particular, and as a result a thrust is produced. So a larger thrust can be obtained but at low velocity, right? So it is just like a diesel engine versus petrol engine. In case of petrol engine, we can get higher RPM or higher speed but less torque. In case of diesel engines, we can get more torque and low velocity at low velocities. So here the major purpose is to attain larger thrust. So by increasing this area, we can get a larger thrust, right? The rest of the process is very much same, 1, 2, 3, 4, but here the turbine work is used to derive compressor and also this propeller. So the net work output available to derive this compressor, this propeller will be given by this equation. Here is the Cp into T3 minus T4. This is the turbine output, H3 minus H4, which is Cp into T3 minus T4 minus this work of compressor. So work of turbine minus work of compressor is the work which is transferred to this propeller, and that is given by this equation. Here you can see a difference. Here Cpg and here it is Cpa. This represents the process in the compressor at low temperatures, and this represents the process in a turbine at a very high temperature, because temperature is already raised to a very high value in the combustion chamber. That's why here this Cp in this process will be a little different than this Cp in the compressor process at low temperature. That's why here it is written as Cpg, specific heat of gases, burnt gases, and this is specific heat of air. It's more like air at low temperature. It is also air but much higher temperature, so Cpg could be different as Cpa. Okay, next we shall see the Brayton cycle with regeneration. Just like we have seen in steam power plant, there was steam power cycle with regeneration to improve the efficiency of steam power cycles. Immediately we can use a regeneration process in case of Brayton cycle here. So in gas turbine engines, the temperature of the exhaust gases leaving the turbine is often considerably higher. So let me show it here. So TS diagram of simple Brayton cycle. This is 1 to 2 compression, heating, yes, expansion, and then exhaust. So this point 1, this is point 2, this is point 3, this is point 4. So in case of gas power cycles, this temperature T4 could be higher than this T2. That is the point here. This T4 could be higher than T2. What is T4? At the exit of turbine, and it is entering into the exhaust, right? And this temperature, if this temperature is higher than this temperature, then we can utilize this heat to heat this air before it enters into this combustion chamber. So that is the logic or behind this regeneration concept of a Brayton cycle. So now let's read. In gas turbine engines, the temperature of the exhaust gas, the temperature of the exhaust gas is this one, T4 at the exit leaving the turbine, is often considerably, not always, but in most of the cases, often considerably higher than the temperature of the air leaving the compressor, then the temperature of the air leaving the, this is the compression process. So this is the point leaving the compressor. So if T4 is greater than T2, then we can utilize this temperature difference to transfer some of this heat to this air before it enters into the combustion chamber. Therefore, the high temperature air leaving the compressor can be heated by the hot gases, hot exhaust gases in a counterflow heat exchanger, which is also called a regenerator or a recuperator. So here is the schematic diagram. So that is clear. That is here are the gases which are leaving the compressor at point 2, and here are the gases which are leaving the turbine at point 4. Now this T4, if it is higher than T2, then heat can be transferred between these two fluids. This one is at higher temperature, this one is at lower temperature. This fluid is moving in this direction, this fluid is moving in opposite direction. That's why it is called counterflow heat exchanger. Yes, here it is shown, counterflow heat exchanger. So both fluids do not mix with each other, but only heat is transferred. Right, so that is the way. So now the entering point to the combustion chamber will not be 0.2, it will be a 0.5 at much higher temperature. So this air which was entering into the combustion chamber at 0.2, now it will enter at 0.5, which is much higher than 0.2. So it means the temperature is already increased. So now you have to supply less heat here, less fuel has to be burnt in the combustion chamber for the same output. So that's how the efficiency can be increased with the help of this regeneration process, and that is shown on this TS diagram also. So 1 to 2 compression, then 2 to 5 represents the heat which is regenerated from the exhaust process is 4 to 6, then 5 to 3 will be the heat transfer in the combustion chamber. From 5 to 3 is the further heat transfer in the combustion chamber by burning the fuel. Then 3 to 4 is the turbine or expansion process. Okay, here you see a 0.5 dash. 0.5 dash represents the maximum temperature of 0.5, because here fluid is entering at a temperature of T4 and this fluid is entering at a temperature of T2. For an ideal heat exchanger, this T2 temperature will be equal to T4. For an ideal heat exchanger, if all of this heat is transferred to this fluid, then this T2 temperature will be T4 here, and this T4 temperature will be equal to T2 for an ideal heat exchanger. So that is that ideal point, that fluid entering at point 2 and leaving at not at 0.5 but at 0.5 dash, and T5 dash is equal to T4. So that is the maximum possible heat which can be transferred in this heat exchanger, so that this temperature T2 rises to T5 and this T5 becomes equal to T4. Then, but in actual heat exchanger, these heat transfer areas are not infinite, so this T5 will be less than T4. The actual T5 will be less than T4. In ideal scenario, this T5 will be equal to T4, and that ideal case or ideal point is shown as T5 dash. Okay, so in this way, by using this regenerator, the thermal efficiency of the Brayton cycle increases as a result of regeneration, since now we have to supply less heat by burning of fuel for the same work output. Okay, so Q regeneration in actual process will be H5 minus H2 or Cp into T5 minus T2. Right, in actual process, that is the heat which is regenerated, Q regenerated. This is the regeneration process. This heat is transferred to this fluid. But regeneration, maximum possible heat which can be regenerated is till 0.5 dash. So then maximum possible is H5 dash minus H2, where H5 dash is equal to H4, because this will be Cp into T5 dash minus T4, and this will be Cp into T4 minus T2, and T4 is equal to T5 dash. That is the maximum possible. So based on this, we can also define an efficiency term for this heat exchanger or regenerator, right? Though the extent to which a regenerator approaches an ideal regenerator is called effectiveness. So now we can define the effectiveness of this heat exchange process or this regenerator process, or effectiveness of this regeneration process. So how it is defined? actual heat transferred during this regeneration process or in the regenerator divided by maximum possible, and actual is given by H5 minus H2 and maximum possible is H5 dash minus H2 or H4 minus H2. So you can replace these enthalpy values. So here is the actual divided by maximum possible. So that is called the effectiveness of a heat exchanger or effectiveness under cold air assumptions. Cold air assumptions means here if we replace here Cp into T5 minus T2 and Cp into T4 minus T2, if we assume same Cp in the denominator and the numerator, it means we are assuming it is at low temperature air where Cp will remain same. So under cold air assumptions, Cp will cancel in the numerator and denominator, so the same effectiveness can be written in terms of temperatures also. Right. So a regenerator with a higher effectiveness will of course give a greater amount of fuel, will save more fuel if the effectiveness of this regeneration process will be higher, because if this heating process will start from 5 dash instead of 5, so this Qin will be even less when the heat transfer process starts from 5 dash. So achieving a higher effective, how we can achieve higher effectiveness? It's simply to increase the heat transfer area. What is this heat transfer area which we have seen here? If we increase this heat transfer area, we can increase the effectiveness of this regenerator, right? Then we can achieve this T5 equal to T4 if this area of heat exchange or area of these pipes during this heat exchange is quite high. But high area means high cost also. So you have to decide about the area of this heat exchange depending upon the cost of this initial cost of this equipment compared to the overall fuel which we will save over the lifetime of this power plant. So that has to be decided based upon these two factors, the cost of this regenerator and the fuel saving. Right, so that is written here in generally. So achieving a higher effectiveness requires the use of a larger area regenerator which carries a higher price tag and therefore causes a larger pressure drop, right? Because as the area of heat exchange is increased means area of pipe is increased. So when area of pipe is increasing, it means pressure drop in those pipes due to the fluid friction is also increasing, right? So it means compressor has to do a little more work because the pressure drop is more because of larger area of pipes. So that's why the use of regenerator with a very high effectiveness cannot be justified economically. If we use a very high effectiveness regenerator, means a very high heat transfer area, unless if this savings from the fuel cost exceeds the additional expenses involved, additional expenses of the equipment or the material of construction of this regenerator. So here now if we can derive the efficiency of this ideal Brayton cycle with regeneration, and that efficiency comes out to be this one. So the derivation is not included in this course, so here I am showing only the final derived equation. So here is the efficiency of Brayton cycle with regenerator. So here you see this efficiency is not only dependent upon Rp and K, the pressure ratio and specific heat ratio, it is also dependent upon T1 over T3. So now we shall understand the meaning of this with the help of this diagram. So the understanding of this equation will be clear with the help of this graph. So here you see a graph. This one is the ideal Brayton cycle without regeneration, and here you see the curves for ideal Brayton cycle with regeneration. So here you have a number of possibilities depending upon this ratio T1 by T3. So for various T1 by T3 we can have various curves of efficiency. Now let's try to understand what these curve means actually. So if I draw the diagram again here. So now let's consider first the effect of pressure ratio for any given T1 by T3. Right. Now if we can, or first let's consider the effect of T1 by T3 for any fixed pressure ratio. Right. For any fixed pressure ratio, for example, this is the pressure ratio. Then we see as the T1 by T3 is increasing from 0.2 to 0.25 and then so on to 0.33, efficiency is dropping. Right. So now what this means, let me show it here again. The ideal Brayton cycle, 1, 2, 3, 4. So here at one particular pressure ratio, if we fix this pressure ratio and K, then we can see the effect of T1 by T3, and which is clear here that as the T1 by T3 is increasing, then the efficiency is dropping, or when T1 by T3 is decreasing, the efficiency will increase for a fixed pressure ratio. So here is T1, right, and here is T3. It means this ratio is actually the minimum, the ratio between the minimum temperature of the cycle and the maximum temperature of the cycle. Minimum temperature is at the inlet of the compressor, and maximum is at the exit of combustion chamber or at the inlet of the turbine. So lesser T1 by T3 means air inlet temperature, which normally this temperature is, for example, fixed. Maximum possible, which is about 1000 Kelvin. So let's try to understand by making T3 fixed at 1000 Kelvin. Now we can change T1. So lesser T1 by T3, T1 by T3, how T1 by T3 can be dropped by decreasing T1 for a fixed T3. So it means less air inlet temperature, which is, for example, only 0.2 times of this T3. If T1 by T3 is equal to 0.2, like here, it means lesser T1 by T3 means air inlet temperature at 0.1 is, for example, only 0.2 times of T3, means more chance of utilizing generator heat. Lesser is this point, the pressure ratio is this one, fixed pressure ratio. So then the difference between 0.4 and 0.2 will be higher, right? Because 0.1 is quite low. If this 0.1 is shifted somewhere here, right? And for the same pressure ratio, this 0.2 will shift here. If this 0.1 is at higher temperature, this 0.1 is somewhere here, then 2 will be here. For the same 3 and 4, this 0.4 will be higher, right? So as the difference between T1 and T3 increases, as the difference between T1 and T3 increases, let me explain it in a different way. Let me draw it again. This is T1, T4, and here. Right. So as the difference between this T1 and T3, for example, this T1 is dropped at the same pressure, right? So this T1 is shifted here, then this T2 will shift here because we are keeping the pressure ratio constant. So this T1 will shift here by decreasing this T1, and T2 will shift here. Now the difference between T2 and T4 will be increased. Here this was the difference between T2 and T4 before. Now when this 0.1 is shifted here, by keeping the pressure ratio same, by keeping the pressure ratio constant, for example 15. So when 0.1 is shifted here, 0.2 is also shifted here. Now the difference between 2 and 4 is increased. The difference between 2 and 4 is increased. It means more chance of regeneration, more chance of utilizing this regeneration heat. So the more will be the efficiency. So now we have understood that for one fixed value of pressure ratio, as this T1 by T3 decreases, means T1 starts to drop. For a fixed T3, the efficiency will rise, as we can see here. As the T1 by T3 is decreasing, efficiency is increasing for a fixed pressure ratio. Now we can also consider one particular value of T1 by T3. Then we shall see the effect of this pressure ratio, right? So now let's keep T1 by T3 fixed. For example, this is T1 by T3, and we see here as the pressure ratio is dropping, efficiency is increasing. So now let's try to understand this with the help of the same diagram. So let me redraw it here again. So as we see here, at lower pressure ratios means the difference between 0.1 and 2 is very low, right? And this is the maximum temperature which we can get, that is T3 fixed at the same 1000 Kelvin. This is 0.3 and this is 0.4, and here you see a difference between T2 and T4 quite high. Now if for the same T1 and the same T3, now by keeping this T1 by T3 fixed, now change the pressure ratio. Changing the pressure ratio means this 0.2 will end up, for example, here at a very high pressure ratio, right? This is new point P2. T1 is fixed, T3 is fixed, right? Here is T3, right? Now this will be new 0.4, right? By increasing the pressure ratio and by keeping the T1 by T3 fixed, what is the end effect? This 0.4 may be less than 0.2. Now there is no possibility of regeneration, to utilize regeneration heat. That's why you see at very high pressure ratios your efficiency is approaching to 0, actually very small, right? By increasing the pressure ratio, this efficiency is dropping, right? So let's see an intermediate point. For example, this 0.2 is shifted here. This is new 0.3. This will be new 0.4. Now the difference between this 2 and this 4 is higher, but still smaller than this point, this 2 and this 4, right? And between the difference between this 2 and 4 is smaller than this 2 and this 4. So with the increase in pressure ratio, the chance of utilizing this regeneration heat drops, and that's why with the increase in pressure ratio for any fixed value of T1 by T3, efficiency drops. So that's how we can understand the meaning of this equation, although we didn't derive, but we can understand the meaning of this equation. Okay, so that is explained here. So regeneration is most effective at low pressure ratios and low minimum to maximum temperature ratios, which we have just discussed. Okay. The next topic is the Brayton cycle with intercooling, reheating, and regeneration. So far we have discussed Brayton cycle, simple Brayton cycle, and then Brayton cycle with regeneration. Now we shall see what are other options to increase the thermal efficiency of a Brayton cycle, and that is if we use intercooling and reheating processes also. So now we shall see how the efficiency of Brayton cycle can be further increased by utilizing intercooling, reheating, and regeneration. So these are all the possibilities which can be employed to further increase the thermal performance of a Brayton cycle. Now, so the basic idea behind these two processes now we shall discuss. This is, we have already studied regeneration. Now we shall discuss first intercooling and reheating. Okay, so let me draw the schematic again. So here we have a compressor, then combustion chamber, then there is the turbine, turbine is attached to the compressor, and here is the exhaust, so here is the inlet. So 1 to 2 process is the compression process, and we know the work output of this turbine, a major portion of this work is actually reused here to derive this compressor. So work of compressor, and WT work of turbine, the total work output of the turbine, minus work of compressor is the net work output which is used to produce electricity, W net out. So it means to increase this W net out, and here is the heat supply Q in. So to increase the efficiency of this cycle, either we have to decrease this Q in or increase this network output, right? So by increasing this network output and by decreasing this Q in, the efficiency of the system can be increased. So now we have discussed in the regeneration process that we can reduce this Q in by utilizing the regeneration process. Now we shall focus on this network output, how we can increase this network output for a given Qn. That is the process which is called intercooling and reheating, which will be used to increase this network output. Now how this network output can be increased, either we can decrease this work of compressor. By decreasing this work of compressor, network output will increase because WT minus WC is the network output, or by increasing this work of compressor. Now both are work devices. This one is work producing device, and this one is work consuming device. If it consumes less work to reach the same pressure P1 to P2, if by some means we can reduce this pressure to reach the same pressure P2, then we can actually increase the network output. If by some means we can decrease this work of compressor. So, and we also know the whenever there is a work transfer, there is a pressure change and volume change. Work done is actually given by the change of P into V, because here pressure is increasing, volume is dropping. Here in this case, pressure is dropping and volume is increasing. So in both of these work related devices, there is a change of pressure into volume. So in case of compression or compressor, pressure is increasing and volume drops. Alright, so it means if for the work of compressor, to reduce this work of compressor, we cannot compromise on P, because for example P2 to P1, this delta P is fixed, right? For example, for a fixed delta P, now if by some means we can reduce this specific volume, then the effect on this work of compressor will be that the work of compressor will drop. Similarly here, in case of turbine, the same PV, here pressure drops and volume increases. So for the same pressure drop from this point 3 to point 4, so for a fixed delta P, for a certain change in delta P, if by some means we can increase this specific volume further, then it will increase the WT, because WT is actually equal to this product PV product. So area under any curve on pressure versus volume diagram represents the work term. In case of turbine, that is the work output. In case of compressor, that is the work input. So in case of compressor, we have seen if we can reduce this specific volume or volume change, the work of compression can be reduced. Similarly here in case of turbine, if we can increase this volume of the fluid during this process, for the same change in delta P, we can increase the work of turbine. So reverse are true. Here we are supplying work and we want to reduce it. Here we are extracting work and we want to increase it. And for the same change in delta P in the compressor and for the same change in delta P in the turbine, now we shall see how we can increase the specific volume here in case of turbine, or decrease the volume of the fluid for in case of compressor, so that here work input is dropped and here work output is increased. So that is the logic behind these two processes, intercooling and reheating. Okay. So what we do here is that let's first discuss compressor. This intercooling is actually linked to compressor and this reheating is linked to turbine. Why intercooling? Because here we want to reduce this specific volume during this pressure change, and here we want to increase the specific volume during this pressure change. That's why how we can increase the volume by heating a fluid, and how we can decrease the volume by cooling a fluid. But here the term is not cooling, it is intercooling, and here is the term is not simple heating, it is reheating. So let's first discuss intercooling. So we can what we can do here, instead of using one compressor, we can use two compressors. So this compressor, one compressor can be replaced with C1 and C2, right? So this single compressor is actually replaced by two compressors. So fluid enters first here at point 1 or P1 pressure, P1. It is compressed to a certain pressure, which is Pi, some intermediate pressure. Then it is cooled here in a heat exchanger, where some cold fluid is brought in contact with this fluid, whose pressure is increased to some intermediate pressure. Here it is cooled means it loses heat to some cooling medium. So here heat is rejected by this fluid when it is brought in contact with some cold fluid. So here its temperature drops, pressure remains same, Pi. Now it enters into the next compressor, where pressure is increased from Pi to same P2. So the same process of single stage compression is replaced with two stage compression, and in between there is intercooling. So now what will happen? So the result is that we have increased the pressure in two steps instead of one single step, and in between we have used an intercooling process. So when pressure was increased here from 1 to I, some intermediate pressure, temperature was also increased, volume was dropped, but now it is cooled here, so volume will drop, right? So volume decreased, but now we further decrease the volume without changing the pressure. At this point, this is a heat transfer process where pressure will not change, only temperature will drop. When temperature will drop, its volume will also drop. So some volume is dropped here with the rise in pressure, but now further volume is dropped here by the drop in temperature, not pressure. Pressure is still Pi. So now volume is dropped further, and now it enters into the second compressor, where pressure is further increased from Pi to P2, but volume was dropped. So that's why the combined work of compressor C1 and C2 will be less than the single compressor for the same pressure rise from P1 to P2, because in between these two compressors we have decreased V, specific volume, and we know that as you decrease V, for the same change in pressure the work of compressor can be dropped. So this particular point, if it is not clear, we shall be discussing it in the next chapter, which is about compressor, and there we shall discuss it in much more detail, and we shall also solve some numerical problems that if we replace one single compressor with two-stage compression with intercooling between these two, the overall work input to these two compressors will be less compared to one single compressor for the same pressure rise, P1 to P2, right? So that is called intercooling. So we can use, instead of one single compressor, we can use two compressors with intercooling in between these two compressors. So overall effect is the reduction in the specific volume. Now let's come here. In case of turbine, we want to increase the work of turbine, and how we can increase? If this P3 and P4 are same, means delta P is constant. For the same delta P, we can increase the work of turbine if we can somehow increase this specific volume. So here, instead of using one turbine, we can use two turbines, just like here, two compressors. So this is point 3, fluid is entering, which is a gas, in first turbine T1, and work is obtained WT1. Now its pressure is dropped from 0.3 to some intermediate pressure Pi, because in the turbine pressure will drop because work is extracted. Now it is sent to the reheater. Reheater in this case is the same combustion chamber. So it is sent back, just like in steam power cycle we used reheating process, where there were two turbines and in between there was reheating and the fluid was sent to the boiler. So here in case of gas power plant, it is a combustion chamber. So here I am showing it, the point 3 at the exit of combustion chamber. Fluid enters into turbine 1, high pressure turbine, where some work is extracted, some pressure is dropped, not till 0.4, some intermediate pressure between 3 and 4, then it is reheated. Reheated means here heat is transferred to the fluid. So pressure will not change, again it's a heat transfer process, but heat is transferred to the fluid, so its volume will increase. Now it will enter into the second turbine, T2. And it will reduce its pressure from Pi to, P4. Right, so Pi to P4. So now pressure is dropped in two increments, P3 to Pi, then it is heated up, reheated, and then it enters into the second turbine. So here we will get WT2, right, and then its pressure drops to P4. So in between we have used reheating. Reheating will increase the specific volume. So that's why the overall work output of WT1 plus WT2 will be higher than this single turbine from this single turbine, because we have increased the specific volume, and by increase in specific volume the more power can be obtained for the same pressure drop. So this is the overall logic to use the process of intercooling and reheating in these simple Brayton cycle to increase the overall efficiency by increasing the net work output of the turbine, and by decreasing the work of compressor. Right, so I have explained it here. Now I will show it, the details on this slide, which you can read it by yourself quickly. So let me remove it all. So whatever we have discussed is written here. The network of a gas turbine cycle is the difference between the turbine work output and the compressor work output, right? It can be increased by either decreasing the compressor work or by increasing the turbine work, or both. So that's why how we can decrease the work of compressor is by using multi-stage compression with intercooling. So the work required to compress a gas between two specified pressures can be decreased by carrying out the compression process in stages. It could be 2 stages, it could be 3, 4, 5 stages, and between every stage there could be a cooling process. I have shown you only a 2-stage compression process with intercooling, but it could be a 3 or 4 stage compression process with intercooling, and that has been shown here on PV diagram also. For example, this was P1 inlet pressure and this is the exit pressure. So this is the line which represents the pressure volume change in one single stage compression. But if we are using 2-stage compression, then it will start from 1 till A, some intermediate pressure, then there will be intercooling at constant pressure, that is PV diagram. So AB represents intercooling. So during intercooling, temperature drops. So now you know how the temperature line look like on PV diagram in gaseous region. Chapter 3 thermodynamics, chapter 3 and 4 of thermo 1. So I will not explain it here again how the temperature line look like on PV diagram. It's all the old concepts, right? So the temperature drops during this process, and now the compression is further taking place from B to D. So here is this area which has been saved, right? Work saved as a result of intercooling process. So we shall discuss this diagram in much more detail in the next chapter. So I will not consume more time to explain this diagram, because here we shall not be solving any numericals related to this diagram. So that's why I leave it here. The further explanation, I will explain it in more detail in the next chapter. But I told you what is the purpose. The purpose is to keep the specific volume as low as possible, because in this PV work we want to reduce, we are actually trying to reduce this speed with this intercooling process. With this intercooling, you can see on the x-axis volume drops. So when volume drops, PV work drops and work input to the compressor drops. So similarly, multi-stage compression with intercooling, we can use multi-stage expansion with reheating in case of turbine. It will keep the specific volume of the working fluid as high as possible. So V will be as high as possible if we are using a multi-stage expansion with reheating in case of turbine. So that will maximize the work output. Here this will minimize the work input. So the steady flow compression or expansion process is proportional to specific volume of the fluid. So specific volume of the working fluid should be as low as possible during compression process, and it should be as high as possible during an expansion process. So now the resulting Brayton cycle, in which we are using intercooling, reheating and regeneration, all of them. So that is the resulting Brayton cycle. Here you see fluid enters again from ambient air, initial P1 in compressor 1. Now it enters into an intercooler where heat is rejected, Q out, right? This is Q out. So 1 to 2 is partial compression, then 2 to 3 is intercooling because fluid is losing heat. Then it is again compressed in the second compressor, right? Then 4 to 5 is regeneration process. At the exit of this second compressor, it is reheated, or it is heated by the exhaust gases, right? Regenerator. Then it enters into the combustion chamber. So after combustion chamber, there are 2 turbines with reheater. So it expands partially in turbine 1, then it is reheated where volume is increased, and then again it expands in the second turbine, and then it leaves as exhaust gases. But before it leaves it into the ambient, its heat is reused here in case of regenerator to preheat this fluid which is entering into the combustion chamber. So now I will draw the TS diagram of this new Britten cycle, which has all the possibilities of utilizing intercooling, reheating and regeneration processes. So let me draw it here. The TS diagram for this complex gas power plant. So let's start from point 1, some low pressure. This is point 1 where pressure, this is the pressure line P1. Now its pressure is increased till point 2 here, 1 to 2, compressor 1. So here you have some, this is another pressure line representing P2. Right, now at this point, at a constant pressure, it is intercooled, or there is a cooling process. So that's why at point 2 its temperature will drop, right? For example, its temperature is dropped again to point 1 temperature, right, and that is point 3. So here it is intercooling. 2 to 3 represents cooling of the fluid at constant pressure P2. Right, and T3 is, in ideal case, T3 is equal to T1, right? So it is cooled but at higher pressure. So when it is cooled, so its volume is dropped. Now it enters into the second compressor. So in the second compressor, again isentropic compression, right? So pressure is increased to 0.4, right? This is 0.4 and this is represent the P4 line, right? Now it enters into a regenerator. In regenerator, its temperature will rise at constant pressure, for example till some 0.5. So 4 to 5 constant pressure heating from these exhaust gases. So at 0.5 it enters into a combustion chamber. So here further the heat is supplied to this fluid, so further its temperature will rise at the same pressure to some high temperature 6. That is the highest temperature in the whole cycle at 0.6. But in the combustion chamber, heat is supplied only during this process, 5 to 6. 5 to 6. 4 to 5 was the heat supplied in the regenerator. But this whole process is taking place at constant pressure. So P4 is equal to P5 is equal to P6. Now at 0.6 it enters into turbine 1, so where pressure drops, right? Partial pressure drop, right, till 0.7, isentropic expansion. So during this process pressure drops. So at this point we have another pressure line, some low pressure line. For example, this is P7. Then at 0.7 it enters into reheater, where heat is supplied to this gas. Q is supplied to this gas, so at constant pressure. So 0.7 till, from 0.7 till 0.8 it will be a constant pressure heating. So 0.7 till some 0.8, for example 0.8 is again this point, temperature is again T8 is equal to T6, but during this process heat is supplied at constant pressure, right? So it reaches the same temperature again as at 0.6, but during this process specific volume is further increased. Now at 0.8 it enters into the second turbine. So here its pressure again drops to the ambient pressure, the same ambient pressure P1. So it will be at the same pressure as P1. So this is 0.8 till 0.9. Pressure drops further in the second turbine. Now from 9 to 10, that is the cooling of this fluid, because it is rejecting heat to this fluid from 4 to 5. So the cooling process will take place from 9 till minimum point could be this one, it cannot be lower than 0.4 because it is losing heat to this fluid at 0.4. So ideally this T4 will be equal to T10. So 9 to 10 represents the heat transfer in the regenerator from this exhaust gases to this fluid 4 to 5, and ideally this 0.5 will be equal to 0.9, T5 will be equal to T9, but actually 0.5 will be a little less than 9, and similarly this 0.10 will be a little higher than 0.4, but ideally T9 will be equal to T5 and T10 will be equal to T4. So that is the diagram for this modified cycle in which intercooling, reheating and regeneration are used, and this area enclosed, new enclosed area is the network output, right? This whole area represents the network output of these two turbines, right? So this was just roughly drawn to explain the individual processes, how those can be shown on TS diagram. So again, you should remember we are not drawing the dome because we are far away from the dome. It is well in the gaseous region, so only pressure lines are shown. And okay, so let me erase it. So here is the diagram which I have just drawn. So now you can practice at your end, and you can see the details from the book also. So I didn't mention any details of these processes. I have just explained, so you can read it from the book by yourself. Okay. So now work input to the two-stage compressor. This is one stage and then second stage. So work input to this two-stage compressor is minimized when these equal pressure ratios are maintained. Means from P1 to P4 pressure is raised in equal increments. Means P2 by P1 is equal to P4 by P3. These pressure ratios are equal. Then we shall get the minimum work input to the compressor. That has been proved actually theoretically, which we will do in the next chapter, that P2 by P1 should be equal to P4 by P3. Only then we shall get the minimum work input to the compressor, right? Similarly, and the same is true here for the case of turbine, that this pressure drop P6 to P7 and P8 to P9, this pressure ratio should also be same to get the maximum work output in case of turbine with reheating, right? So it means for best performance P2 by P1 should be equal to P4 by P3, and similarly P6 by P7 in turbine 1, the pressure drop in turbine 1 should be equal to P8 by P9, which represents the pressure drop in the or pressure ratio in the second turbine. So the back work ratio of this gas turbine cycle improves as a result of this intercooling, and this is intercooling and this is reheating process. 2 to 3 is intercooling and 7 to 8 represents the reheating process, because during reheating volume increases, work output increases. During intercooling volume drops and work input to the compressor also drops, so that will increase the back work ratio. But it does not mean that with the help of this intercooling or reheating the thermal efficiency will definitely improve. For a definite improvement in thermal efficiency, this process of regeneration must be there, because this is very important. Without any regeneration processes, all these lines will be very close to each other. This gap which is created here, it is only due to this Q regenerated. So that's why intercooling and reheating always will decrease the thermal efficiency unless they are accompanied by regeneration. So only intercooling and reheating processes are not enough. Regeneration process should also be there. Only then, with the combination of regeneration, intercooling and reheating, we shall get a definite improvement in thermal efficiency. Next topic is combined gas power cycle. So I will not read these details, we will just describe it with the help of this diagram. So to further increase the thermal efficiency of a thermal power plant, whether it's a gas power plant or steam power plant, here is one way. Because normally in gas power plant, the temperature of the gases which are leaving the turbine are quite high enough, because here in the combustion chamber of this gas turbine, the temperatures are well above 1000 degrees Celsius. So here after expansion, this temperature could be very high, around 500 degrees Celsius, and that is enough to make steam, right? So here we are using a heat exchanger not as a regenerator but as a boiler for this power plant, which is a steam power plant. So here these gases, the exhaust gases of this gas turbine, can be used as a boiler for a low pressure or for a low temperature steam power plant, because here we need temperatures around 500 to 600 degrees Celsius, which can be achieved from the exhaust gases of this simple Brayton cycle. So with this way, now it is a combination of steam and gas power plant, where the exhaust gases of this gas power plant is used as a heat input for the steam power plant, right? So now with this way, the efficiency of this combined system may reach up to 50%, right? So for very large power plants, such systems can be used to have a huge increase in thermal efficiency. And increase in thermal efficiency simply means the saving in the overall fuel input. So fuel is only burnt only here, so a part of its energy is extracted here, the remaining energy is used here in this heat exchanger, which is acting as a boiler for this steam power plant. So here is the TS diagram of both cycles. So you can see here this represents 5 to 6 and 6 to 7, 7 to 8 and 8 to 9 represents the Brayton cycle, right? This portion. And here at point 8 temperature is significantly high compared to this point 2. So that's why there is a heat exchange. From point 8 to point 9 temperature drops of these exhaust gases, but at the same time temperature of this liquid water increases till point 3. Point 3 is a little less than point 8, right? Maximum it can reach till point 8, right? So this 2 to 3 process is taking heat from this process 8 to 9. This dome is shown only for water. For this gas, which is air, the dome is not here in this TS in this T temperature versus entropy scale. The dome for air is somewhere here, right? So this dome is only for water, for this working fluid, and for this fluid the dome is cannot be shown here because the dome is far away from this region. So this region, in this region, water is maybe liquid or mixture or a gas, but in the same region of temperature and pressures, this blue line, which is representing air, will definitely be a gas. So that is the combined gas and steam power plant, which can be used to increase the overall efficiency. So that has been explained here, so which you can read it by yourself, but the main thing is the understanding of this schematic and this TS diagram. We shall not be solving any numerical problems related to this, so hopefully also only the theoretical understanding should be the requirement for this course. So here is the pictorial view of the same gas and steam power plant. So here is the gas power plant, air is entering into the compressor, right? And then here is the combustion chamber, for example natural gas, and then hot gases are entering into the gas turbine, right? And this turbine is also mounted on the same shaft as of the compressor and the generator. The hot gases leaves here and now enters into this heat exchanger. What is this heat exchanger? This heat exchanger is acting like a heat recovery boiler for this steam power plant. So here one fluid is these hot gases coming from this gas turbine. The second is the fluid coming from the condenser, liquid water, and it is here heated up with this gas at very high temperature. Now it becomes steam and enters into a steam turbine. So in this steam turbine, work output is achieved, and it is used to derive this generator. So we get work output from this generator and also from this generator, and that is the electrical output. So after expansion in the steam, it enters into a condenser. In the condenser, there is some cold fluid, for example cold water, which takes up this heat of condensation. Then it goes into the cooling tower. What is cooling tower? Cooling tower is another heat exchanger where ambient air is flowing. So this water is separated over this surface, and from the bottom some air is flowing, ambient air. So there is a heat exchange. So water which has taken this heat in the condenser, it will transfer this heat to this air, and air will leave. So during this process some water may evaporate. So to compensate for this loss of water due to evaporation, this makeup water from the nearby river, canal, or whatever is the storage can be reused. Anyway, so this is just the pictorial diagram of this whole gas and steam power cycle, right?